guys, welcome back to today's session. Now, today's session is going to be a little bit different in the fact that I'm not going to have any text associated with it. So what I'd really like for you to do as we go through the slides today and what we're talking about, I really want your lights off in your room because I want you to get a full flavor for the pictures that I've got on here. And like I said, we've been talking about evolution of stars. We're going to go through looking at protostars all the way to the next it may take us 1 or 2 sessions. I'm not sure how long it's going to take to get all the way through the end of stellar evolution and looking at black holes. And then the section after this, what I want to do is go back and put on then the final details dealing with what happens as those stars evolve off the main sequence. Like I said, today what I want to do is just kind of give you a feel for what's going on out there within our galaxy and the evolution of stars. So like I said, guys, please go turn your lights off, sit back, relax, and enjoy these pictures and kind of think about what's going on as we talk about how stars are formed. So let's go ahead and look at stars from the time that they were born, guys. Now, the first picture that I have on there is not a picture of a star. It's a picture of a galaxy, and this is a spiral galaxy. And the reason that I have this picture particularly is to go ahead and show you where the spiral arms are on this galaxy. I think you can see the core of the galaxy, and you see these big spiral arms coming out, and you see a lot of pink material, pink nebulous material that's in the spiral arms. Well, that's really where within our galaxy we're going to find a lot of this stellar evolution, a lot of these new stars that are forming, and it's because you've got a lot of gas and dust in those spiral arms. We will eventually talk about, well, in fact, in the next chapter or next unit, talk about galaxies, and we'll talk about spiral galaxies and elliptical galaxies. And elliptical galaxies do not have hardly any star formation going on because they don't have any gas and dust in them, whereas you get these really cool spiral galaxies that have lots of gas and dust in the spiral arm, and so that's where you indeed see stellar evolution going on. Now, remember we talked about the fact that you have these cold, dark molecular clouds out in space, and that's what's going to go ahead and form our star? Well, here you have a dark, cold molecular cloud. It's extremely thick in terms of the dust and the gas that's in it, and that's why you can't see through that. I think you can see a little bit around the edges where it's not quite as thick, and man, by the time you get into the center, you can't see anything at all. And there's very little really hot blue stars around it, so we don't have any other kind of reflection or emission type nebulas around here. But those are the kinds of clouds that are going to go ahead and form stars. Now, first of all, they're not going to form just one star. We're going to have open clusters or clusters of stars formed out of these dark clouds. And the other thing, keep in mind that they have mostly hydrogen and helium with a little bit of other heavier elements, and those are elements then beyond helium. All the stars that you see around it are stars within our galaxy. Now, I've just got several other pictures to show you relative to these really dark, cold molecular clouds. And the reason they're called molecular clouds is because its temperature is cool enough in there so that hydrogen forms H2 as opposed to being an ionized hydrogen ion. Now, you're going to start seeing blue nebulas, some red nebulas, some green nebulas, things like that. Our blue nebulas are called reflection nebulas, and they're made out of a lot of gas and a lot of dust. And the dust grains within those blue nebulas are reflecting and scattering the light off, kind of like the same reason that our sky is blue when we look at it. It's because it's scattering then the shorter wavelengths of light, the blues and the violets. Well, that's exactly what's going on with these reflection nebulas. But that does imply that there's some kind of really hot blue star nearby so that you're getting that light being scattered by that nebula. But you can see around here on this picture that other dark material. We're going to find that that's an area that you're going to have stars being formed. And yes, guys, it is a problem because they're very, very dark, and it's going to be a while before we can actually see those new stars. It's another dark nebula with, you can see some really hot blue stars behind them so that you're seeing those reflection nebulas. Remember, all the stars that you're looking at are stars that are within our galaxy. So remember, guys, we've got lots of stars there. That nice blue hot star, that's providing the energy and the light for that reflection nebula behind it. If you look at the upper right, you see a star that's already gone off and has formed a supernova or a nova. And remember, guys, that we talked about something has to go ahead within these cool, dark clouds to go ahead and get that compression in there to go ahead and start causing the cloud itself to go ahead and collapse. So we're going to come back to that when we talk about those mechanisms, and I show you some examples of them. It's another nice dark nebula with a nice little reflection nebula down there at the bottom. And we know these are places where you get stellar birth. The other thing I want to point out to you is if you look over kind of toward the center left and up a little bit, you get what looks like clouds that are going to have protrusions on them. Think of a slug with the antenna coming up there. Well, that's going to become very important because we're going to find that those antenna-like projections then will tend to go ahead and hold a new protostar. Another gas and dust cloud out there in space that we know has active stellar evolution going on. And remember I said you had some other kinds of gas and dust clouds out in space? Well, you're seeing a red one and a yellow one. You're still seeing that blue one. A lot of times that's reflecting the chemicals that are making up that cloud. And so if you look at that red one, the yellow one, you're really looking at emission-type nebulas. So they've got some kind of bright hot stars behind them that are causing that gas to glow. And when it glows, it gives off that energy. And so remember, guys, when we talked about specters and emission spectrums and absorption spectrums, this is nothing more than the energy that's given off like you would have during an emission nebula. So you get those bright, very bright lines that say we're looking at an emission spectrum. So the reds, the colors are simply due to the various distinct transitions within the atoms themselves that are forming that. But remember, these nebulas are hot nebulas as opposed to those dark nebulas which were very cold. Lots and lots and lots of new stellar birth within our galaxy. And we feel like not only with our galaxy, but every other galaxy that we look out there that has a lot of gas and dust. So you're now starting to look at very young stars. And remember, guys, in terms of how we got there. Now, these are stars that you already see out there. This is the Orion, the constellation Orion. Remember, guys, we talked about the middle star in Orion's sword is not a star, it's the Orion Nebula. And that is certainly some place where we know we have had stellar evolution going on. And so if I look at that area, then within that Orion Nebula, I see these pictures that I've shown you. And if we look at the bright, the Horsehead Nebula is a very dark nebula where we know we do have had stellar evolution. Same way if I look then more toward the center of that and the trapezium and things like that, we know that we've had very active stellar birth. Just some bright clouds again, right along, showing you that gas and dust within the Milky Way galaxy, within looking at one of those spiral arms. Again, very, very, very dusty, very gassy, but that's what you want if you're going to form new stars. Just kind of a close-up of a little bit to the right of where we were looking before. Doesn't seem to matter in what direction we look. We see new stars forming. So that's not something that is very unusual. It's something that happens all the time and almost in a continual cycle. Now, let's talk about, and remember what I told you, when you have a new star that's formed, you have these big, huge molecular clouds. And remember, guys, these things are massive, okay, light years across. And so when we go ahead and have stars form in there, we very rarely just have one star. A lot of times we have then these open clusters that are forming. Now, you have to have something that's going to cause the initial collapse. And what you see right here is a compression wave gas bubble is basically moving through space. And when that runs into these molecular clouds, it's going to start then that cloud to collapse. And that's what you want to go ahead and form a star. You've got to have that cloud, and you've got to go ahead and collapse it, and you've got to increase its density. And that does that by gravitational collapse. So I can have something through here. Here's another gas bubble that is being driven outward by these nice hot stars that are in there. And as soon as that runs into these giant molecular clouds, it's going to start pushing those atoms and molecules around. And if those atoms and molecules are moving around and they're jostling and they get close to each other, they're going to start sticking or holding together because of gravitational attraction. And the more mass I have, we've talked, the more mass it can attract. And eventually, it's going to start rotating and even attracting more mass. Now, once we've got that cloud that has been pushed some way so that, again, it's got the initial trigger mechanism to start it to collapse, you know that it's going to go ahead and continue. Now, picture I just showed you right there was basically the remnants of a supernova. Remember, I also said that a supernova, because of this massive explosion that occurs, can also go ahead and start that cloud to collapse. And so I've got a YouTube video that I want you to watch. It's very short. I'm actually going to start over again so we don't have that writing in the middle there. But you've got a star. Now I want you to look at the power that's associated in this when it goes ahead and starts going off. And think of that spreading throughout then our part of the Milky Way. And notice the incredible pressures and temperatures that come out with that. So we're forming all those other elements that are going to help make new stars. And then that energy gets radiated out, which can run into those big molecular clouds and go ahead and start new stellar evolution. So let's talk about these stars. I said that you originally have the collapse. And once you've got that collapse down, you start going ahead and converting potential energy into kinetic energy. So potential energy, remember, is energy of position. Kinetic energy is energy of motion, and that kinetic energy then is seen as heat because those molecules start heating up, they start moving around more, and we find out that then the stars, well, actually the cloud at this point, it's not a star yet, is also, because of that motion, just start rotating. And the cloud starts out at a really, really, really large radius, and eventually, as it gathers more mass, it's going to collapse down, and due to the conservation of angular momentum, remember that skater that I showed you, and she brought her arms in over her head, and therefore she decreased that mass relative to her axis of rotation, and so for the conservation effect of that to happen, that star is going to, or that cloud is going to start rotating faster. Well, it starts rotating faster. You still got a collapse going on. You still have that potential energy being converted into kinetic energy. Kinetic energy then is seen as heat. And so when I start looking at these stars within these clouds, I can't see them in visible light. However, I can see them because of the heat in terms of infrared light. And if you see those little red dots on my picture, those little red dots are what are turning into the protostars, which will eventually go ahead and turn into the star. Now, the other thing that happens as these stars go ahead and continue collapsing down, remember we talked about this hydrostatic pressure. You want the pressure to be equal from the pressure coming in to the pressure going out. Well, we find that, we've got this cloud that is collapsing down to become a new star, a protostar. And it's collapsing down, it's collapsing down. Well, what happens is at some point, if you want the star to continue to collapse, energy has to be given off. And that's what you're seeing in this infrared part of the sky. So this, like I said, was not taken with a visible telescope. It was taken with an infrared telescope. And so if you want that star to collapse and not stop, not reach that equilibrium condition, then energy has to be given off. And so it's given off in that infrared part of the spectrum. Now, so that energy gets given off, therefore the cloud can go ahead and continue to contract. Just same kind of thing. Those bright red images that you're looking at are new stars. And so you're looking basically at a stellar nursery right here. Now, the star is going to continue, that cloud is going to continue to collapse. At some point, it's going to become opaque. I can no longer see it. It's no longer radiating that energy. Okay? Now, what happens at that point, as we've talked, the star now, or that cloud, can now go ahead and continue collapsing, but now you're going to start really increasing the temperature and increasing the density within the core of that cloud. At that point, guys, we really talk about that as being a protostar, a star that will eventually become a star. It's no longer that collapsing cloud. It really has its own identity. It actually, you can tell, is a protostar at that point. Okay? Now, goes ahead and continues collapsing. It goes ahead and continues then increasing the density. And we're heading towards some point where we can start converting hydrogen into helium, but we haven't quite made it there. Okay, this is just another stellar nursery that you're looking at, and you're looking at those really bright stars, those new stars. Now we also find that, and this is just a conception, artist's conception of that drawing, as that cloud is condensing down, and so you see that main kind of clump in the center. Okay, that's what's actually going to form our protostar. And so that's why I said you're talking about these clouds that are really large, that are condensing down and almost forming these layers as I go down. And then within there, you might also get smaller little clumps that we're going to find are going to form the planets. You see in the lower left, that one of those dark molecular clouds, and then there's a little bit better picture of it to the right there, and you can almost see that really big part of the cloud that has been then condensed down to form that protostar. Now, a protostar still does not have the temperatures necessarily high enough within the core, nor does it have the pressures high enough within the core to start converting hydrogen to helium. So we haven't formed a star yet. We've just got that protostar. And we find a lot of times these protostars are found in big columns of gas and dust. Okay, and so I want you to imagine that the center of that big column is what's going to become a new star. Right now it's a protostar. And as that protostar goes ahead and is in the process of collapsing down and, getting to where it has the temperatures and densities high enough to convert hydrogen into helium, it's going to start blowing winds away. Okay? And remember, guys, you always have all these other stars around there that are doing the same thing. And so basically why this is a column as opposed to any other shape is the rest of that area around it, the rest of the nebula around that star has been blown away by the other stars surrounding it. And the only reason that you still have the column left is that column has been protected by that star in there, and so it hasn't been blown away. Although eventually I'm going to show you that it does go away as well when that star actually settles down and becomes a star. Now that's what these next series of pictures are. This is the Eagle Nebula. You can see those big columns, and this is what I'm saying. Remember that you have more than one star that kind of forms in there. Imagine that to be a little bitty cocoon in there on those columns, and that's where we're going to have that protostar become a star. And as you look at that in infrared light, that's where you're seeing those bright little pink dots, which are going to become the new stars. This is just a close-up of the Eagle Nebula and some of the areas that are in the process of forming those stars. And you can see that you have columns in that material because you have so many other stars around there. Again, it's getting blown away. But remember, during that time, and it can take any place between 1 million, to 50 million years, just kind of depending on size. And remember, guys, the larger the star, the shorter the time it's going to go ahead and take to collapse down and form. And also, we're also going to remember, or going to find out, that when we looked at that HR diagram, and we looked at how long those stars stayed on the HR diagram, that the larger the star, the faster it evolved off of that main sequence line. So guys, if you're really big, you're going to kind of go through life really fast. Just another one of those, this is actually called the Eagle Nebula Fairy. You know, you imagine that you've got that new star right in the center there. Now guys, these things are light years across. Please don't think that these things are, you know, the size of our solar system. These are light years across. Very, very, very large. And remember, you're having to take that cloud from being a very, very, very large cloud that is, again, you know, light years across, and it's got to collapse down into something like what we see with like our star, like our sun. So it does take a while to collapse that down and to go ahead and cause those core temperatures and pressures to be reached. Those little protrusions, you're still kind of looking at those stars, those protostars that are in the process then of forming. I personally think that looks like a snail kind of moving its way through the galaxy. But when you realize how large that snail is, guys, it kind of boggles the mind. Another picture taken in infrared. You're seeing those bright red stars show up that will become stars. Now, we also know, when we look at stars, that right before that star completely and totally settles down, that there are lots of gases and jets of wind that are given off. And it's just in that process of that star reaching stability. And so here you see a star that's almost there. You see the original cloud that it was formed out of, or at least the original section of the cloud that formed the stars. And then you see these gas and jet protrusions that are coming out. Now, keep in mind, guys, when I show you here in a few minutes these planets that are forming around these stars, man, those gas and jets, I mean, they're coming out at sometimes 500,000 miles an hour or more, can wreak havoc on planets that are really close to that star. Now, these are two very young stars. The one on the left is what's called our T-Tauri winds, and that happens right before that star actually, that protostar becomes a star. And you can see those, although it's a little hard to tell what the speed is right there, but again, we're looking at speeds that are, you know, approaching 500,000 miles an hour or more. So if I'm, let's say, Mercury, and I'm really close to the sun, and our sun, you know, sends off these winds, I can literally blow the outer parts of Mercury away. And we think that's what happened to some of our planets. You know, if they were close enough to be caught in these T-Tauri winds, then yes, that's definitely a problem. And we know that the T-Tauri winds occur right before that protostar settles down and behaves itself nicely as a star in the main sequence line. Now, the one on the right, you can see, is also giving off energy and giving off material, but it's giving it off very specific. It's parallel to the poles. So it's giving off, and there's a jet of gas being given off at the North Pole and one that's being given off at the South Pole. And we think those are driven by very, very, very strong magnetic fields and magnetic pressures, simply because of the fact that you have this magnetic field around this star, and that star is rapidly then moving and rotating, and so it forces it then to go ahead and come along basically the magnetic field. I mean, think about where on our Earth, where you have the magnetic field that tends to meet. It goes from the North Pole to the South Pole. That's exactly what's happening here, and so that material is getting then pushed out or expelled outward right along the poles. And this is what's called bipolar flow, and we see it not only in new stars, but we're also going to see it when we look at what happens with black holes at the center of our galaxy, as well as black holes at other galaxies. And then we're also going to see that bipolar flow when we look at neutron stars and how they're rapidly rotating. And that'll be an evolutionary sequence we look at when we talk about moving off of the main sequence line. Now, remember I said that you have these protostars, and from the fact that you have this material that is condensing down out of this cloud, well, this is probably a picture of an early solar system. That center blob is what's going to become the star. And you have these other blobs around there that are going to become the planets. And remember we had that conservation of angular momentum? And so that means everything's going to be rotating around in the same direction. And so those little clumps that will indeed manage to survive and become a planet are all going to be rotating around that central star. Now, as we've talked with the planets, you know there are things that within our solar system that aren't all necessarily orbiting in the same direction. Or you may have things that are spinning opposite, because we did have some events during that early part of the solar system where we did have things run into, Venus and other planets like that. But this is probably one of the better pictures of an early solar system that we have. And we know now the fact that solar systems are probably out there a lot. At one time, we thought a star usually formed a binary star or a triple star system and didn't go ahead and form planets. Nowadays, we think that planets are extremely common out there. Just another picture within a cloud that is a very active birthplace, and you look at those little sections and you will see that nebulous material that is forming that what eventually will be the star, and you see that planetary disk around there, which is where your planets indeed are going to go ahead and form. Like I said, guys, it's certainly not something that's uncommon. Nowadays, we know that there's lots and lots and lots of planets out there. Same way here, I'm looking at that central disk that's going to become that protostar, which will eventually become the star, and you see those little other clumps in there that will become a planet, if it survives. Those T-Tauri winds can definitely blow a planet away if it's close enough. Now, guys, once we have that star, that's a protostar, that cloud that is condensed down into that protostar has continued to collapse, and at some point, what's going to happen is the pressures and the temperatures within the core are going to get hot enough to start converting hydrogen into helium. And so you have new stars. And so this is a picture of brand new stars. Okay? Because now that hydrogen is being converted into helium, you have energy given off. That star is burning through the process of nuclear fusion, in which case you are taking small nuclei and building up larger nuclei. And for normal stars, it's going through that proton-proton chain. It's a really large star, then it's going to go through a proton-nitrogen carbon chain. But we get stars of all different masses formed within an initial cloud. And that's the really nice thing, to be able to look at these clusters of stars, in the fact that we do make the assumption that for the most part they all formed at the same time. They formed out of a cloud that has a nice same composition all the way throughout. So the only difference that we see when we look at those stars, and we can look at their evolutionary sequence, is the fact that they started out with different masses. And based on that, it's going to show where they end up on the main sequence line. And from that, and they've evolved off the main sequence line, we can follow it based on mass. But I still think this is pretty cool in terms of the picture of stars, because you get all these really nice hot blue stars, as well as all those other stars that you see in the background. Just some really nice hot blue stars, and some of the material that's left over from what formed them. If I look at this picture, again, you can still see that kind of dark nebula material. You see those really hot blue stars, and those hot blue stars are surrounded by reflection nebulas. It's kind of like the stuff that's still around after that star formed. And so a star becomes a star when it starts converting hydrogen into helium through thermonuclear reactions and starts shining on its own power. Now, remember I said that those stars, when they go ahead and form, and they've got these T-Tauri winds, or just simply the radiation pressure of the star itself moving outward, well, you tend to go ahead and thin out that gas and dust from which it started around that original cloud. And so, I don't know if you look at that, and it kind of looks to me like you've got a big skeleton out there. Kind of see those eyes that have been cleared out, and kind of that mouth that's still in the process of being cleared out. Well, that's exactly what happened, guys. You had stars that formed. The radiation pressure outward, as well as at those T-Tauri winds, just basically blew everything away. Now, the cool thing about this is if this happens in a big enough cloud with enough stars, then you're going to start more collapsing of the original cloud, that giant dark molecular cloud, and you're going to form new stars. So it's almost a self-perpetuating mechanism. With what's going on, you got these really big stars that form. They radiate pressure outward. It kind of goes ahead and thins then that cloud out. That cloud continues to jostle around, runs into more, and you start the process all the way over again. Just more examples of what used to be dark molecular clouds that are now very active in stellar evolution. You have all these brand new stars, and as those brand new stars are in the process of forming, they do go ahead and basically blow away the material that they formed out of. And for our case, it looks really cool in the sky. Now, this is just an example of a cluster of stars. Because like I said, you do end up forming clusters as opposed to just individual stars. And all those clusters, they tend to be moving around their common center of mass. Just another smaller cluster. Actually, a really small cluster. You can see that there's some nice hot blue stars there, as well as some that are probably a little bit smaller, not quite as blue. So you see a color change in there. Remember, I form more smaller red ones than I do really hot blue ones. Now, like I said, this is a really small cluster. There's a little bit larger cluster. You can see that they're all relatively close together. That's because they all formed out of that same cloud. Now, some of them, especially on the edges, may kind of get kicked out. They are simply far enough out from the center, that common center of mass, that they aren't held in, and so they can go wander. And we call those wanderers. But for the most part, all those stars are going to stay around their common center of mass. This is H and Chi Perseus. These are two double star clusters in the constellation Perseus. You can see they formed relatively about the same time, out of really, really, really big, massive molecular clouds, because there's a lot of stars in those two clusters. Just another open star cluster. Now, we'll find out that these things do indeed go ahead, as we've talked, and form right within the spiral arms of our galaxy, because that's where you have a lot of that gas and dust. And in fact, these things are so new that you still have some of that material that's there that's left over. It hasn't completely been blown away. Although you see some of that pinkish material, that certainly has thinned out. And you can almost see those really hot blue stars embedded in there that's actually causing that material to be spread out. Just another very, very, very young star cluster. Now, this star cluster happens to be the Pleiades, and so you've got the moon in there. And guys, if it is shining on the right side, think about what phase of the moon that has to be in. If you told me it was a crescent phase, that's great. If you told me that it was a waxing crescent, that's even better. Okay, so I've got then the Pleiades right there. Now, let's look at the Pleiades in a little bit more detail, and that's what I get when I look at the Pleiades. Remember, guys, I said that you can go ahead and observe this in the winter skies. You can kind of look up, and if you don't stare at it, you can kind of see this fuzzy little cluster. Kind of looks like a little hazy spot there in the sky. It's up a little bit to the up and to the, if you look at Taurus the Bull, looks like it's up and a little bit to the right of Taurus the Bull. And we know it's a young star cluster. It's very, very hot blue stars that we're seeing here because you have that material that's left over. And so if I look at even better picture of it, that's all that material that's left over from when those stars formed. And this is a reflection nebula. So you have those really bright, hot stars that are then heating up and sending out their energy. It runs into that gas and dust cloud, and that dust within this cloud then goes ahead and scatters the light, and it scatters it as blue light, because blue light and violet light have shorter wavelengths than all the other colors. And so remember, guys, you're scattering the blue light first. This is one of the newer pictures that came out from NASA. Notice the detail on that. to really go ahead and start bringing out not only the original stars themselves in the Pleiades, but also all that material that is left over from when those Pleiades formed. And so we know this is a relatively young star cluster. Now this one is a little bit different, and I put this one in because I wanted to show you that those stars excuse me, do have color associated with them. I mean, we see those really hot blue ones better, but you really do get stars of all colors and all shapes, all sizes formed within that original cluster. And so these are just star trails that have been spread out toward the end to go ahead and show you the color a little bit better. You can see there's definitely color associated with those stars. Now I put this picture in to show you what I think it might look from the Earth if we were actually in one of those clusters, those open clusters that had a huge number of stars in it, or maybe even a globular cluster. Now this is actually a picture taken from the Earth, guys, so what in the world are we looking at if that's probably not all those stars in there? Well, actually, guys, what you're looking at is you're looking at birds. Imagine those birds have just taken off and they're flying in the sky, but the person that took this was also an astronomer, and so like, hey, wait, if I kind of played with this a little bit, that would remind me of what we would look like if our sun indeed was part of an open cluster and you had lots and lots and lots of stars above us. You know, we'd hardly ever really have a completely and totally dark sky because all those stars would be there. So guys, really looks good, but it's really a cluster of birds and not a cluster of stars. And so the last couple of slides I have are just really looking at the stars that we have out there. And for the most part, when we look out there, those stars are behaving themselves. They're on the main sequence line. And as we've talked, that means they're converting hydrogen into helium. And they're doing it for generally a really long time. Okay? And then what happens after they evolve off that main sequence line? What happens when they finally run out of hydrogen and they can no longer go ahead and produce helium because there's simply no hydrogen left? Well, that's what we are going to start on our next session. We'll look at what happens when those stars evolve off the main sequence line. And I'll go ahead and I'll look at really massive stars. I'll look at massive stars. I'll look at stars like our sun. And then we'll also talk about those little red dwarfs that are the very bottom right hand of the main sequence line. Because every one of them are going to behave differently when they evolve off of the main sequence line. And that's where you're going to get these massive explosions in terms of supernova explosions. We're going to look at what our sun is going to do, which means we're going to be looking at forming a planetary nebula, which, by the way, guys, has nothing to do with planets. But we form these really cool planetary nebulas. And what's going to be left at the core of that planetary nebula? What's going to be left at the core when that supernova goes off? And we will talk about spiral galaxies and elliptical galaxies and all those kinds of things in the next unit then when we talk about cosmology and then the universe itself. So this will get us then to stars that were on the main sequence line. Remember that we're converting hydrogen into helium. So what I want to do next time is do the same pictorial view then of what happens when we talk about stars evolving off the main sequence line. And so we'll look at planetary nebulas, and we will look at supernovas, and we'll finish with what happens when you have a star that forms a black hole. So with that, guys, I will plan on seeing you next time, and we'll go for what happens then.